In this video, we will present the double sideband modulation, one of the variants of amplitude modulations. The modulated signal is relatively simple. In particular, it's much simpler than the modulated signal in a conventional amplitude modulation. In a conventional amplitude modulation, we have the carrier plus an scaled version of the modulating signal times the carrier. The scaling factor is the modulation index divided by the range of the modulating signal m of t. Now, in a double sideband modulation, we only have the product between the modulating signal m of t and the carrier, a much simpler expression. We avoid this scaling factor, but what is more important is that the introduction of the carrier is avoided. And this means that the drawback of a conventional amplitude modulation of having a relatively low power efficiency is eliminated, because now in a double sideband modulation, power is not going to be wasted to transmit a carrier that in terms of information doesn't carry information. This is one of the characteristics of this signal. There is a price to pay for this power efficiency. Here we have an example of a modulating signal m of t. Here we have the carrier, and now the modulated signal for a double sideband modulation is just the product of the carrier with the modulating signal that here is plotted in a different scale. Now the product is the blue curve that we have here, and this is the shape of the modulated signal for a double sideband modulation. Now the envelope of this signal is sometimes proportional to m of t and sometimes is proportional to minus m of t. Therefore, an envelope detector will not be able to recover the information. The modulated signal in the time domain is very simple. The analysis in the frequency domain is easy, because now we have a product in the time domain, we have a convolution divided by 2 times pi in the frequency domain. The convolution between the Fourier transform of the modulating signal and the Fourier transform of a cosine. The Fourier transform of a cosine are two deltas, are minus omega c and plus omega c, and then the convolution with these deltas basically is shifting the Fourier transform of the modulating signal plus omega c and minus omega c. And this is the spectrum of the double sideband modulated signal for a deterministic signal m of t. Compared with a conventional AM, we don't have the two deltas that were the Fourier transform of the carrier, and we only have the shifted replicas of the frequency response of the modulating signal of m of j omega shifted plus and minus omega c radians per second. There is also no scaling related with the modulation index and with the range of the modulation. And again, we have two sidebands, and as for a conventional amplitude modulation, the bandwidth of a double sideband modulation is twice the bandwidth of the modulating signal, twice W radians per second, or 2 times B in hertz, but twice the bandwidth of the signal that is transmitted. This can be easily seen in the frequency domain with a very simple graphical example. For instance, if this is the Fourier transform, an example of the Fourier transform for a modulating signal, a Fourier transform that is a rectangle between minus and plus the bandwidth of the signal, we have in the spectrum two shifted replicas of this Fourier transform. One of them is shifted to omega c and the other one is shifted to minus omega c. But it is straightforward to see that now the bandwidth of the signal is given by this shifted replica is 2 times the bandwidth that we have for the modulating signal m of t. And this happens independently of the shape of the Fourier transform of M. Here we have another example for the Fourier transform of the modulating signal. Now a triangle between minus and plus the bandwidth, but again, the bandwidth of this shifted replica that we have here is 2 times the bandwidth that we have for the modulating signal.